Hello everyone, welcome to Math 143 College Algebra. Well, we have to do a recap, of course. We had 5 ways of thinking of a function. 5 ways to think of a function. We're going to say rule. What do? You say f of x equals x squared plus 1. So we have the idea of a rule. We have the idea of ordered pairs. And what might some ordered pairs for this function be? Well, maybe 0 and 1, right? It's a set of ordered pairs. Maybe 1 and 2, maybe 3 and 10. Does that sound right? And presumably some more. Let's just say there's a whole bunch of them. I'm not going to list all of them. What was our third way? Well, if I have a bunch of ordered pairs, what could I do? I could graph those ordered pairs. So we can have a graph, and here comes my graph of my function. And what do? I locate 0, 1, there it is. And I locate 1, 2, there it is. And I locate 3, 10, there it is. Not exactly to scale, but it's not bad. And I would do that for so many points, and I would get that thing. I don't want to take up all that space. I'm going to fiddle with this just a bit. Good enough. You can see the parts you need to see. What was our fourth way? Fourth way was a map. And so in the map, you have these kidney-shaped blobs. I don't know if that looks like my kidney, but you have points in them. Maybe you have 0 and you have 1 and you have 3, and then over here you have other points and the map, and you can label it, this is set A and this is set B, and here's my F, and 0 goes to 1 and 1 goes to 2 and 3 goes to 10. You should be having this strong feeling of deja vu. And then there's a machine, right? And I'm not going to take the time to draw it. You know what it looks like. You put it in the machine, and I always make those noises, ker-chunk, 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 and you're turning the crank on the machine, and you put in a 0, and ker-chunk, 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 and out comes a 1, and so on, and so on, and so on. 5 ways to think of the inverse of a function. And that's actually the title of Chapter 5, Section 1. It's called Inverse Functions. And the first way you can think of the inverse is as a rule. And we would write f inverse. And let me talk about this notation for a second. I think of all the notations in math, and some of them, remember in general, I have that silly thing that I say, among all the tribes of humankind, mathematicians are the laziest, and because they're lazy, they're always coming up with new notations, and those notations aren't meant to confuse undergraduates. The notations are meant to simplify their lives so they don't have to write a lot of stuff. For example, if you just look at f of x, it's a function, and it acts on x, and what you do is you square x, and then you add the value of 1, and then you assign that to, that's a lot of words. If I had to write all of that out, it would kill me. And so if I can just write f of x equals x squared plus 1, and even this x squared, that's a notation. You had to learn it. Well, it's easier than writing x times x, and that's why they do it. Almost all mathematical notation comes from a desire to be succinct and clear. We don't want to have to write out a lot of stuff to express our ideas. And if you remember that, when later you encounter new and strange mathematical notation, you'll go, oh, what are they really trying to do? Oh, they just don't want to write, and there's some long thing that you could have written. So you kind of have to learn it. You just grin and bear it. You go along with it. There are different notations for different things, and some of them I think are pretty clear, and some of them a little less so. I think that this particular notation for the inverse of a function, and this is the standard notation, I think it's the ugliest, most undeserving thing. Oh, I just can't say enough bad things about it. And the reason is, in math, we have this little -1 that you put up in the air, and you'd say, oh, it's an exponent, it's a -1. Yeah, except it's not. This is not a reciprocal. That is not an exponent, not an exponent. And so to emphasize, this is pronounced f inverse. I put it in quote marks so you know f inverse of x. So you know this is the pronunciation. Don't ever let me catch you, don't ever let anyone else catch you saying f to the -1, because that is totally, totally wrong. Why did they choose this? I don't know. Well, who chose it? Gary, you know the history. Yeah, I wish I knew. I would go after that devil. I'm sure the person's long dead, so there's not much I could do about it now. But it's really, really, really ugly, and all I can say is smile nicely at the ugly person, at the ugly notation, and try not to make a scene. It drives me nuts. It shouldn't be that notation, and once in a while it will confuse us, and we'll curse imprecations muttered under our breath and go on about our lives. So what can I do? I didn't invent it. You just have to live with it. The f inverse of x is, and then you can think of something, right? You could say the square root of x minus 1. So there's a rule. Cool. How about some ordered pairs? Well, definitely you can think of the inverse of a function as ordered pairs. Over here we had 0 and 1, we had 1 and 2, we had 3 and 10, we had a whole bunch of ordered pairs, and if someone wanted to be particular about this, they could specify for you, you know, this 0 and this 1, that's an x and a y, and see this 1 and this 2, those are x and y, and see this 3 and this 10, those are x and y, and all you have to do to get an ordered pair list for an inverse is to flip it. And so watch how much brains this takes. I had 0, 1. Now I have 1, 0. I have 1, 2. Well, now I have 2, 1. I used to have 3, 10. Well, now I have 10, 3. And I used to have a whole bunch of things. Well, now I have a whole bunch of things, and every one of them has the x and the y flipped. Does it actually work? I don't know. Let's try it. Plug in a 1. So here's a 1. Plug it in. 1 minus 1 is 0. Take the square root. I get 0. Oh, yeah. Okay. Try the 2. 2. Plug in a 2. Subtract 1. I get 1. Take the square root. Yeah, it's still 1. There it is. Yep. 10. Take the square root. So not yet. 10. Plug it in. Subtract 1. I get 9. Take the square root. I get 3. Oh, yeah. Huh. Okay, so you can express an inverse as a rule. You can express it as a list of ordered pairs. Of course, you could express it as a graph. And all you have to do is flip x and y. Should I say flip? Maybe I should say switch. That's a little more English. Switch x and y. Here I am going to say flip x and y. Well, so here's my graph. The original graph has this nice U shape, and what I'm going to do to help me is I'm going to draw a little helper, and my little helper is going to be the line. Can everybody tell what this line is? And this is kind of to scale. This is the line y equals x. And if you say, wait a second, y equals x? Yeah, y equals x. What about it? Well, if y equals x, then x equals y. Yeah. Well, if you flip x and y, oh yeah, if you flip x and y, then y equals x, and x equals y, and it kind of makes sense. But we will use this. In the past, we've had, what have we had? We've had symmetry, right? This is symmetric across the y-axis, and that means horizontal symmetry. And we've had symmetry across the x-axis, and that was a vertical symmetry, right? Well, now we're going to have symmetry across this y equals x line. And so I'll take some point, look over here at this blue graph again, and you think of a point like 0, 1 right there. Well, it's going to flip over the line. Imagine your imaginary line there, and it becomes 1, 0. And similarly, 1, 2, it becomes 2, 1. So it's flipping over this line that you can't see there. And 3, 10 becomes 10, 3. It flips over that line. And so we get a shape. It was 0, 1, and now it's 1, 0. And you can see, because you can think to yourself, there's where 0, 1 is, and now here's where 1, 0, and you see, yep, it just went straight across that line. And then we had a point at 1, 2, 1, 2, and it went straight across this line. It became 2, 1, 2, 1. And then we had 3, 10, and it goes straight across the line. The line's right here. It goes straight across that line. It becomes 10, 3. So that's way out here. 10, 3. And you go like that, and yes, it's symmetric across the, look at this. Look at the blue guy. He's symmetric across the y-axis. Well, yeah, but now we switched x and y. So now he's symmetric across the x-axis. Okay, so draw him in. Isn't that pretty? Can you do a map? Yeah, you can do a map. You're not going to be impressed by this. There's nothing fancy about it. By the way, this is the complicated version. If I were lazy, and you know I am, if I were lazy, what I would have done is I would have just redrawn this exactly the way it is, and then I'd just drawn my arrows going the other way. So instead of the arrowhead being in B, I'd have the arrowhead being in A. Here I actually switched them, you know. That's like overkill. What a lot of extra work, Gary. And then what about the machine? Well, the machine it's this cool machine. We used to have this cool machine that you would drop in a 0 and you'd go kerchunk, kerchunk, kerchunk. You'd turn the crank and out would pop a 1. And you go, whoa, look at that. A 0 turned into a 1. Hey, try it again. Drop the 1 in, see what happens. And kerchunk, kerchunk, kerchunk. And you know, it comes out a 2. Well, this machine, you take that 2 and you put it in and you go kerchunk, kerchunk, kerchunk. All the machines make the same noise. It doesn't matter what they do. And out comes a 1. And you say, whoa, a 1 came out? Put the 1 in, kerchunk, kerchunk, kerchunk. And out comes a 0. And whoa, that's kind of cool. So there are all sorts of applications for these inverses, and we'll learn more about them here in a minute. But if you start with these are 5 ways to think about functions, you can think about, you can undo the function. That's the idea of the inverse. If something goes in and something else came out, well, this does the backwards, the reverse, the inverse. It undoes it. Most of these kind of make sense. The graph kind of doesn't. We'll talk about that in a split second. The machine in particular makes sense kind of, but kind of not. In particular, I can think of a cake making machine, and it takes as its input, you put in a couple eggs and a cup of sugar and a couple cups of flour and just a little bit of oil and maybe some baking powder, baking soda, whatever it is, and you stir it all up. You put it in the machine and kerchunk, 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 and out the other end, hey, you've got a cake. Whoa, that's cool. I know about that machine. I've seen machines like that. I do not know of any machine that you can put a cake in one end and go kerchunk, 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 and it goes through this conveyor belt and out the other end. There's this bowl and it has a couple eggs in it and a cup of flour, a cup of sugar, and a couple cups of flour. I don't know that machine that undoes a cake. Sorry.
The time machine.
Oh yeah, if it were a time machine, yeah. And as I say, I don't know about time machines. I have a time machine. I mean, don't be telling people about this because it's kind of a secret. You know, the government would be after me if they knew about it. But I have this machine. It's in my closet, and it's really, really cool. I go into my closet, I close the door, and if I stay in there for a minute, then when I come out, it's a minute later. I'm in the future. I'm a minute. Yeah, right. Stupid, Gary. Of course, if you go in for a minute, yeah, but it's a time machine. I go in, and when I come out, it's later. I'm in the future. Yeah, right. So anyway, if you can figure out, maybe there would be a use for that. I'd rather have the cake than all those ingredients, but maybe you wanted to make something else. I was going to make breakfast, and all I have is this cake. Well, put it in the undo the cake machine and you'll get your eggs back, and then you can fry up some bacon and toss the eggs in, and won't that be fine? Okay, so there's the machine. There are practical problems with having a machine, and that's, as I say, it's a practical thing. That's for the engineers, not for the mathematicians. How about the graph? Well, the problem with the graph is I have this function. I started with a function, and then what I did was I was able to graph it. And if all I have is the graph of a function, and sometimes that is all you have. Sometimes you don't know the rule. You don't have a specific list of ordered pairs, and it's hard to tell from the function, right? How thick is that line, and what's the scale exactly? And sometimes you can't tell. But with any graph, you could flip it over this reflecting line. You know, it goes all the way. It's this diagonal line, 45-degree line. You could flip it over that and get this graph. The only problem, if you look at this graph, you say, wait a second, Gary, hold on, hold on, hold on. Well, the problem is that when we learned about graphs of functions, we learned how to, when we first learned about functions, right? This was a big deal when I first did this thing. We learned a rule called the vertical line test. And the vertical line test says that if a vertical line, an up and down line, goes through 2 points on the function, well, then it's not a function, right? Because a function, we had a definition of a function. A function is a rule that assigns to each value of x exactly one value of f of x. And so you can only get one thing out. If you have a machine and you put a 3 in, it doesn't matter how many 3s you put in, you always get a 10. That's how it works. Well, here, if you look at this and you say, okay, so if I put in a 10, I get out a 3. Yeah, great. Put in a 10 and you get out a 3. But then what's this extra line? This line says that if you put in a 10, you get a negative 3. And you think, well, that can't be right. You can't get two things out. If you put in a 10, you have to get out a 3. You can't get out a negative 3. So what's wrong with this? The problem is this fails the vertical line test. This so-called inverse isn't actually a function. This is not a function. It fails the vertical line test. Well, we will fix that in a minute, but I want you to look at this and kind of admire it and think of the order of it and how, not the ordered pairs of it, just that, gosh, there's like this back and forth. And that's kind of the idea of an inverse. It's a back and forth. You put in an x and you get out a y, and then later you think, I want to put in the y and get my original x back. I was happier before I traded. And this does that for you. Let's fix the graphing problem. And what was our problem? Our problem was if f of x equals x squared plus 1, we know that looks like a parabola. And we know from chapter 4, chapter 3, wherever those transformations were, we know that we have to shift up 1. And so this isn't hard to sketch, right? You know, you go up 1, yep, there you go. Cool, what a nice parabola, Gary. And then what's the problem? The problem is that when we look at the inverse, it didn't work. So let's redraw it the way I did, and I'll even put the orange line in, and then we'll fix it in a second. No, my hand doesn't shake like that. You think I'm old? And it doesn't. It's because of this tablet and this stylus, and it does weird things. I look at it and I think, looks like how my grandpa used to write just before he died. Yeah, well, thanks. Yeah, what a good guy my grandpa was. Anyway, yeah, and we've noted two problems. The inverse fails the vertical line test. I wish I had known that before I flipped it. Wouldn't it be nice to know ahead of time that it's not going to work? And you could say, hey, don't bother. You know, you draw this and you draw this and you put all these dotted lines and what a lot of trouble. And then you draw this and I had to draw it twice because the first time I did it wrong. And if someone had told me ahead of time, we need that time machine. If someone had said before I did all of the work and said, hey, don't bother. It's not going to work. It's not a function. Well, then I would have saved myself a lot of time and trouble. And you think, well, how would I have known ahead of time that this would fail the vertical line test? Well, what is the vertical line test? The vertical line test is y is changing, y is changing, y is changing, y is changing. What's the idea of these inverses? Is I've swapped x and y. So if here y is changing, y is changing, y is changing, how about I go back to my original graph, my original function, and I say, x is changing, x is changing, x is changing, x is changing. And you think, oh yeah, the original, this isn't the second problem. I should have indented. The original fails the, what is it? It's a horizontal line test. Sure, because I swapped x and y. Y is vertical direction and x is the horizontal direction. So you can actually look at any function like this one. Hey, Fred, look, I got a function. Yep, looks like a function. And how do you know? Because it satisfies the vertical line test. And then you ask Fred, hey, Fred, do you think we could make an inverse of this function? And Fred will say, nope. And you say, why not, Fred? And he says, because it fails the horizontal line test. Don't bother doing this because it's not going to work. So there's one problem solved. Let's do that. First problem. What's the second problem? The second problem is, I really, really want it to work. Well, we can make it work. And you say, no, you can't make it work because look, it fails the, right? If I've got a point right here, well, I have a point right here because there's a symmetry. Okay, so erase half of it. We can make it work by restricting the domain. So let's do that. Second version. See, I've restricted my domain, and what does this look like? It looks like this, right? Because don't do any negatives. Start at 0, and then go to the right. Go to the right. And now, well, our first question is, does that pass the horizontal line test? And you go, horizontal line, I only hit one spot. Horizontal line, I only hit one spot. Horizontal line, I only hit one spot. Yeah, it passes the horizontal line test. That means it does have an inverse, so here you go, second version. You're going to think I'm cheating here in a second. What does this function look like? And you say, well, it's a square root of something. Oh, I know what the square root of something looks like. I memorized that. It looks like that. And what does the -1 do? It shifts it 1. Well, which direction? Well, negative, oh, it's inside. I'm moving it to the right. It feels backwards. I'm moving it to the right. So I'm going to move it to the right. And I get this. And is this a function? Well, vertical line test, pass, pass, pass. Yeah, vertical line test seems to pass. I'm only hitting one spot. And so, yeah, this works. It does work. And then this is why I say, why you might say I'm cheating. Gary, those look exactly the same. Yeah, they do look exactly the same. This isn't really a graph of this. This is a graph of I flipped this. Is this really the inverse of this? Well, no. Why? Because this doesn't have an inverse. Look at it. It fails the horizontal line test. If you restrict the domain, well then, yes, this is the inverse of this. And there's a graph of that inverse function. Is that too subtle? Is that too quaint? You get the idea. I kind of cheated at the very, very beginning when I said this was the inverse. Well, it's not the inverse because this doesn't have an inverse. It's kind of like the cake. There's no way to undo the cake. Riley, you probably have a question that'll clear everything up. Please ask it.
So do we restrict the domain every time it does not work when the inverse fails the vertical line test?
I told you you would explain everything. That's exactly what we do. So you will have exercises where they'll say, what is the function, what's the inverse? And one of your choices will be, it doesn't have an inverse, and you'll know. And then if they say, okay, come on, couldn't you please, pretty please with sugar on top, make an inverse? Well, then you restrict the domain. What else do I need to talk about? Oh, you probably want to know how to create one. No, that's not the first thing. There's two other things I need to talk about. One thing is, well, wait, what about this domain and range? And this is kind of a neat thing. Conceptually, it's kind of neat. When I explain it, you'll go, oh, neat. And then when you see what sorts of problems they have, you'll go, ugh, why do I have to? And it's not because they're hard, because none of them are hard. It's just you feel like you're typing and typing and typing, and MATLAB won't leave you alone. And what that is the domain. So let's go back to our original function. Original function, second version. What was it? It was f of x equals x squared plus 1, restricted to 0 to infinity. And I might just ask you, well, let's sketch it just so it's really easy for us. What's the domain? I'm thinking the domain. Well, come on, Gary, it's written right there. Oh, yeah, okay, well, I guess that makes it easier, doesn't it? And what's the range of the function? What does it extend to? And I'm thinking, well, it starts right there, which is 1, and then it goes up. Should I even label this point just to simplify our lives? There's 0, 1. And yeah, we start at 1, and then it goes up, 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 up as high as you want to go as long as you keep going to the right. Well, that was cool. Let's look at our inverse, and I'm going to write function, second version. Second verse, same as the first. I don't remember where that's from. Some old rock and roll song, some old pop song. What's the domain? Well, there are a couple ways you could do it, right? One way to do it would be, well, just look at the graph, silly. Okay, I'm looking. It goes from 1 to infinity, I guess. The other way would be to what? Would be to use our algebraic tools. We have graphical tools, we have algebraic tools. Later, depending on what class you're in, you'll have numeric tools. But let's try algebra. And you say, well, algebra, if someone asks me the domain, I just assume it's all real numbers. So someone says, what's the domain of? I say, all real numbers. And they say, come on, I haven't finished the sentence yet. What's the domain of this? And I say, oh, well, it's all real numbers except, and what were the rules? We had 2 restrictions. We will learn a third in this chapter. Oh, isn't that exciting? But the 2 we know is, well, you can't divide by 0. There's no division in this problem, so that doesn't even apply. And you can't take the square root of a negative. Oh, look, there's a square root. So x minus 1 has to be greater than or equal to 0. So if x minus 1 is greater than or equal to 0, yeah, I could even do it. X minus 1 is greater than or equal to 0, so x is greater than or equal to 1. Oh yeah, I got it. It's 1 infinity. And then how about the range? And you have to think about that. You know, usually the domain is easier to find than the range. And you have to think, well, if I put in a 1, that's as low as it goes. So 1 minus 1 is a 0 square root. So I guess 0 is the lowest. And you can also look at the graph and say, look, it's going from here to here, right? It starts at 0 and it goes up, 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 up as long as you want. And so the range seems to be 0 to infinity. And what you might notice, I'm hoping you've noticed this, is, hey, look, the domain of the inverse, 1 infinity, that's the range of the original function. And the range of the inverse, 0 to infinity, that's the domain of the original function. And yep, the domain and ranges are flipped. And then you think about it a second, you go, oh, of course, because what? The domains here, these are the x's. And the range here, these are the y's. And I flipped the x and the y's. So of course the domain and range are flipped. So let me put that in your notes. Notice the domain of a function is the range of its inverse. And vice versa, you know, vice versa all different ways. Vice versa. That means backwards too. So the range of the function is the domain of its inverse. If you only knew the domain of the inverse, well, then you know the range of the original function, and so on. It goes back and forth. I didn't want to write out the whole sentence. If you want to in your notes, that wouldn't be a bad idea. Oh, I got to give you one more vocab word. A function is 1-to-1 if it passes the horizontal line test. The idea is if you got something out of it, then you know what went into it, because it's one thing to one thing. But you'll see in the exercises where they'll say, is the function 1-to-1? And you think, how would I? What it means is, does it pass the horizontal line test? And you know about transformation, so you can kind of draw them in your mind. You can see what they look like, close your eyes and see the function and think of whether it passes the horizontal line test. And if it does, it's 1-to-1. If it is 1-to-1, then it has an inverse. Only 1-to-1 functions have inverses. And that makes sense, because if it's not 1-to-1, well, then it's going to fail the vertical line test once you flip it. Not only any 1-to-1 functions, only 1-to-1 functions. I left out the word functions. It's kind of hard to talk and write at the same time. Only 1-to-1 functions have inverses, and every 1-to-1 function has an inverse. Sometimes it can be hard to figure out what it was. You know, this one was nice because, well, Gary just told us. But suppose Gary didn't tell us, then how would I find the inverse? Yeah, that's a really good question. I'm so glad you asked. Let me get a new screen here, and we will see how to find the inverse of a function. Step 1, of course, is, well, can you? And what that means is, sketch a graph or imagine the graph in your mind. Make sure that it passes the vertical line test. Horizontal line test. How to find the inverse of a function. The book doesn't say this, but I'm going to say it. Check that it is 1-to-1. If it's not 1-to-1, well, then don't bother. You're wasting your time. There isn't an inverse. Example. Find the inverse to f of x equals, let's use x squared plus 1. That'll work. So check that it is 1 to 1. Nope. Well, okay. New example. Find the inverse to f of x equals x squared plus 1 on a restricted domain. Okay. Yep. Okay, then we're on to step 2. I think this is step 1 in the book. Some of these steps are very, very mechanical. Rewrite f of x, because it's a function, so they give you f, and maybe it's g of x or m of x or h of x, whatever it is. Rewrite it as y. So this step does not take any brains at all. Right? I look at this thing, I say f of x equals x squared plus 1. Cool, I write y equals x squared plus 1. Whoa, that took some brains. No, it didn't take any brains at all. Okay, is there more? Yeah, there better be, because we haven't found the inverse yet. Then what? Swap x and y, and you think, well, yeah, that's what an inverse does. It swaps x and y. So over here, I'm going to swap. I have a y. I'm writing x. I have an x squared. I'm writing y squared. So again, that didn't take a lot of brains. I had to pay attention just a hair, but not a lot. I swapped x and y. Now's the part finally we get to do some work. Solve the equation, because that's an equation, right? It has an equal sign in it. That makes it an equation for y. Okay, so there's y. If I'm solving for y, I need to isolate y, right? That's what they always say. Subtract 1 from both sides. I get y squared equals x minus 1. Cool. I better take the square root of both sides. Okay. I'm going to switch it just so it looks sensible. I'm going to put y equals the square root of x minus 1. There you go. The square root of y squared is y, so that takes care of that. And the square root of x1 is the square root of x minus 1. Last step, rewrite y as f inverse of x. That weird notation. And I write f inverse of x equals the square root of x minus 1. That's how you do it. This is a skill you will have to perform several times in today's exercises. Yeah, the book version has 4 steps because they don't check it first, but you know, you have to check it. When you're done, you should probably check it, right? You've seen me, I have a certain penchant for checking. I really liked to check. I hated it when I was a kid. But nowadays, you know, you saw me do it. I tried the 3 and saw what it did. Oh, it turned into a 10, and then plug in the 10 here. So just pick a couple little values and try them. What would happen if I, try it out. Let's try one. Let's put in a 2. Okay, put in a 2. 2 squared, that's 4. Add 1. 5, cool. Try putting in a 5. 5, subtract 1, I get 4. Take the square root. It's 2. Oh, I like this. Let's try a negative 10. Yeah, I don't fall for that. We're not doing negatives. Oh, okay. You could do a positive 10 if you want. 10, square it. It's 100. Add 1. 101. Well, let's try this. 101 minus 1, 100. Take the square root. 10. Oh, that's what I started with. Cool. So you can always check these. And in fact, we can generalize that. Fun fact to know and tell. If f of x is 1 to 1, then its inverse is unique. There's only one inverse. It's not like, well, there's 3 different inverses. Nope, there's one. And has these interesting properties. You don't have to say interesting, but they're kind of interesting. F of f inverse of x equals x. And similarly, inverse of f acting on f of x equals x. And if you'd rather write it, you know, you can write these compositions. That's called composition. We learned that already. If you want to write it with that little O, the little 0, the circle that's kind of above the line, you could do that. The book does that. Let's try it. Ooh, yeah, let's. Okay, let's try it. There's an exclamation mark, so you know this is going to be fun. What did we have? We had f of x equals x squared plus 1, and we had a restricted domain. And we figured out just a few minutes ago, using that algebraic technique, this is x minus 1, the square root. So let's do f of f inverse of x. The only hard part of this problem is writing it out. And remember, my shortcut, my technique for getting these right is I draw f, right? I use placeholder parentheses. What does f look like? F looks like something squared plus 1. Something, I don't know what, squared plus 1. So I have written the f. What does f act on? F acts on the inverse. Well, what does the inverse look like? It looks like the square root of x minus 1. Right in the square root of x minus 1, it's set up, and then I say, what is the square? The square of a square root, well, they cancel. Those are inverses. Square root and square root are inverses. And so we write x minus 1, and then what? Plus 1. We get x. Cool, that worked. Should we go the other direction? Yes, you always should. And the reason is it's possible that it doesn't work both directions. That's very, very rare. I don't think the exercises ever give you one. And so if you can recognize this sort of problem, you could cheat on it, right? Because it says, hey, what's this and this? And you try it and you go, oh, it's x. Huh. And then they say, well, how about, and they give you the other direction. And you will be tempted to say, and it's x too. And what I encourage you to do just for the practice of the algebraic manipulation is go ahead and do it. And I will model that excellent behavior by doing it myself. So what am I going to do? I'm going to I'm going to draw what f inverse looks like. F inverse looks like the square root of something minus 1. And so I use my placeholder parentheses. It's the square root of something, I don't know what it is, minus 1. And what is the something? Well, it's f of x. What does f of x look like? It looks like x squared plus 1. So notice, setting these up is really, really nice. I don't have to use any brains. So square root of, well, don't I have to simplify that first? Yes, it's a PEMDAS rule. So x squared plus 1 minus 1, well, that's x squared. And what's the square root of x squared? It's x. You could, if you were that sort of person, say, don't you mean the absolute value of x? Yeah, right, isn't there a rule for that? And yes, except I happen to know that I'm only positive. X has to be, it can't be negative. So I don't need the absolute value signs. And anyway, that's what I was hoping to get. Hey, I got x again. So this rule was satisfied. If I go either direction, I get my original x. And I didn't have to try it with 10. You know, I did it with 10. And we did it with, what, 2? You know, oh, 2, it becomes 5. And 5, oh, it becomes 2. Oh, it works. Well, it works for 2. But how about 2.5? Well, okay, well, give me a minute. 2.5 squared, it's 6.25. And then add 1, it's 7.25, and then go the other way. And you could do that, but you still are just trying different values. And maybe there's a value that it doesn't work on. Well, yeah, but we did it not for a particular value, but for a general value of x. And we found that if you plug in an x and it goes through this machine and then it goes through this machine, you get back your original x. And if you run them in the other order, plug in an x and go through this machine and then go through this machine, you get back your original x. And it doesn't matter what x is. This is for any particular value. So you will have to do things like that let's try it activity in your exercises. Let's do a hard one. This is as hard as they get. Find the inverse of f of x equals 5x minus 3 over 2x plus 1. This one's hard. Remember, you have 5 steps. The first step is to think of the graph, and you think, we never learned how to graph this one, Gary. You might use Desmos, yeah. If you do use Desmos, you'll see that, oh wait, we do kind of know this. Anyway, you might try Desmos and satisfy yourself that it does pass the horizontal line test. You might try a couple values, you could throw in, okay, let's throw in like 0. 0 is always a good one. Plug in a 0, then 5 times 0 is 0, minus 3, it's negative 3. 2 times 0, it's still 0, add 1, it's 1. It's negative 3 over 1, that's negative 3. Okay. You might throw in a 1. Okay, 1, 5, minus 3 is 2 over 2 times 1 plus 1. It's 2/3. You could do a couple in your head just for the fun of it. The hard part on this one is the algebra, right? The step when I say, now solve for y. So let's do the rest. First step is to rewrite f of x as y. So y equals, and well, that was hard. No, it wasn't. I didn't use any brains at all. And then what's the next step? Swap x and y. Okay, there's a y, I'm writing x. There's a 5, there's an x, I'm writing y. There's a 3, there's a 2, there's an x, I'm writing y. There's a 1. That didn't take any brains either. Now solve for y. Well, that's kind of a pain. And the reason is, well, there's 2 different y's. So what I will have to do is get all the y's together. Eventually, I will reach a stage where I have to combine like terms. And I can't do it yet. And why can't I do it? Because there's an ugly fraction, Gary. That's what makes this one hard. Well, clear the fraction. Multiply both sides by 2y plus 1. So here's an x times 2y plus 1. And here's a 5y minus 3. If you are that student who wants to write in your notes, multiply both sides by 2y plus 1, then please do that, because otherwise you'll look later and you'll think, how did he get it? It's hard to write with this tablet, so I sometimes write a little bit less than I would. Now what? I'm going to put in 6th grade lines for you. I'll make them orange. Hey, there's one. Hey, there's one. I've got 2xy. I'm just going to write x2y. That's what I'm going to do. X times 2y plus x equals 5y minus 3. So what's the trick now? Move all the y's to one side. Usually the left. That's what people traditionally do. So what do? I look and I say, well, there's a y. Yep, I see it's a y. It's on the left. I'm leaving it on the left. I'm rewriting it as 2xy. And then I see an x. Well, that's not a y. Well, then move it. How do I move it? I make it negative. Negative x. See, I moved it. There was a plus x on the left. Now there's a minus x on the right. There's an equal sign. I'm done with the left. Here comes a 5y. Wait, that's a y. I need to move the y's to the left. How do I move it? I make it negative. Minus 5y. There was a plus 5y on the right. Now there's a negative 5y on the left. There's a minus 3. Well, it doesn't have a y in it. It's minus 3. Well, then just leave it where it is. Minus 3. Cool. Now what? Factor out the y. Because everything on the left has a y. So there's the y. I just factored it out. And what's left? Well, I did have a 2x times a y. Well, then there must be a 2x left. And then you have a minus sign. And I did have a 5 and then a y, so I'm factoring out the y. I'm left with a 5. And now divide. I'm left with a y on the left, and on the right I have a negative x minus 3. That's what I had. And I just divided by 2x minus 5. What's the last step? Rewrite y as inverse. F inverse of x equals, and I'm just copying. This step doesn't take any brains. And just so everyone can see what a good job I did, I'll put a box around it. So, check. What was it we did? We put a 0 in. F of 0 equals, and we tried it out a minute ago, right? And you think to yourself, well, the x's don't even play if it's 0. So let's just say negative 3 over 1, it's negative 3. I remember that now. The inverse of -3. I'm feeding it back in the other machine. And so what do I have to do? I have to say -3 minus minus makes a plus. Okay, let's write it out. Negative something minus 3 is 2 over something minus 5. I'm using placeholder parentheses so I don't have to think and I don't have to get confused. On the top, minus minus makes a plus. The reason why we won't discuss. It's a positive 3. Minus 3, well, 3 minus 3, I'm thinking that's 0. If I were lazy, I'd quit now. But I want to be careful. I just want to make sure I didn't break it. If this bottom were also 0, well, then I screwed it up. But the bottom is -6 minus 5. The bottom is -11. And now I can safely say, yep, if I put in a 0, I got out a 0 from the inverse. And so it worked. And, you know, you could try 3 more if you wanted. I don't think you want to, because what did I do? I put in a 1, and I got 2/3. And do you want to put 2/3 in there? No. It's weird fractions, yeah, and would you get back a 1? Yeah, you probably would. -3 2/3 over 2/3, 4/3. Yeah, it comes out to 1. It works. Cool. So there's a whole bunch of stuff about inverse functions. I think I hit everything in the book. I don't think I did it in quite their order. Of course, that stuff about 5 ways of thinking about it isn't in there at all. That's not something they give you. Oh, they give you something called relations. Think of relations as ordered pairs. I don't think you even have to know it for these exercises.